Welcome to the second lecture video in our Class 12 time series of lecture videos. We'll be looking at an antimetric excess, so this concept of optical purity or an antimetric excess in this video, and we'll also show you that levorotatory and dextrorotatory compounds, it doesn't really have anything to do with R or S stereocenters. So to begin, consider a sample solution where an enantiomer plus A has specific rotation alpha of 50 degrees. How can you make a solution of plus A and minus A that has an observed rotation of 25 degrees? And so this gets directly to our ideas of percent optical purity and enantiomeric excess. So we define percent optical purity as our observed rotation alpha over a specific rotation of a pure enantiomer times 100%. And in this case, where we want a solution with an observed rotation of 25 degrees, that means we have more plus A than we do have minus A. So we put 25 divided by 50 times 100%, that's 50%. And we can also define this as the enantiomeric excess, or EE. So a 50% EE solution. And so how would we make that? Well, graphically, here we go. Say you have a solution and you divide it into 4 parts. Well, to get a 50% optical purity or 50% enantiomeric excess, you actually have to have 3 parts plus A and 1 part minus A if you want that 50% enantiomeric excess to be in plus A. Because the 1 part minus A cancels 1 part of the plus A, and then in terms of the whole solution, you're left with a 50% enantiomeric excess. So the general equation, if you have 1 enantiomer in excess, say it's plus A, it would be plus A minus minus A divided by plus A plus minus A, all times 100%, and that's just the enantiomeric excess for your solution. We know that the whole solution is made up of all of plus A plus minus A, so we define that as 1. In our case, we've got 0.75 of our whole solution as plus A minus 0.25 of our solution as minus A divided by 1 times 100% is our 50% enantiomeric excess. So hopefully that's clear. We can definitely try a practice problem at some point, maybe in the class time itself. D and L are used for dextrorotatory and levorotatory. It just describes the direction in which light is rotated. So L is a negative sense and D is a positive sense. There's no relationship between D and L and R and S stereocenters. So for example, let's take L, S minus phenylalanine. At 25 degrees, its specific rotation is reported as minus 32.7 degrees, depending on your literature source, at a concentration of 2 in water. And so, L-phenylalanine is probably going to be pretty soluble in water. It's an amino acid, another one that we rely on for our proteins. We can do a reaction where we change this carboxylate group, we esterify it, so we change it to an ester. And this is something we'll actually look into in terms of mechanism, and we'll discuss in terms of carboxylic acid derivatives in the second semester. The way we would do it is we would add methanol and a little bit of strong acid catalyst like HCl. And so we could end up with this methyl ester of L minus phenylalanine. And in fact, its specific rotation at 20 degrees and the sodium D line is plus 32.4 degrees. That is in a different sense than its carboxylate starting material at minus 32.7. And so this is, like I said, a concentration of 2 in ethanol now instead of water, because once you convert it to methyl ester, it's not so water soluble. So both starting material and product have the same stereocenter. The direction that light is rotated, L to D, changed though. So L and D don't have anything to do with what our stereocenter is, because our stereocenter stayed the same between our starting material and our product. But the way that light was rotated definitely changed. And that concludes this video. We'll see you for the next one.